Good afternoon. Today I will be presenting the major findings and recommendations from my white paper, Mitigating Pilot Fatigue in Commercial Aviation through Data-Driven Scheduling and FRMs, which will be explained shortly. This paper examines one of the most persisting human performance challenges in modern aviation, pilot fatigue, and outlines actionable research-supported strategies to address it. Fatigue has long been recognized as a contributing factor in aviation accidents, but in recent years the issue has become more pressing. Commercial flight operations have extended, international networks have grown, and airline scheduling practices have been increasingly complex. Even with existing duty time regulations, fatigue-related impairments continue to surface in accident investigations, line operations safety oddities, and confidential pilot reports. Research from NASA, ICAO, the FAA, and the NTSB consistently emphasize the same core point. Legal compliance does not necessarily equal physical readiness. A pilot can fully meet regulation rest requirements and still be operating at a reduced level of alertness due to circadian, that's going to be a hard word, I'll stumble on a bunch, trust me, circadian disruption, sleep inertia, accumulated sleep debt, or operational stress. In fact, multiple studies indicate that fatigue contributes from 20 or 30% of human errors in flight aviation incidents, affecting everything from reaction time, attention and judgment management, and decision-making under pressure. In the opening section of the white paper, I examined several structural changes in the industry that elevate fatigue risks. These include the increasing number of ultra-long haul routes, more frequent use of back-to-back early morning or late-night duty periods, and the heavy reliance on reserve pilots, who often receive irregular rest opportunities. Pilots also report challenges as inconsistent layover environments, insufficient sleep opportunities between close-spaced legs, and the destabilizing effect of rapidly crossing multiple time zones. When these factors accumulate, the result is predictable. Cognitive performance declines even when the pilots have met all official rest minimums. NASA's research on circadian lows demonstrate that performance effectiveness can fall by over 30% during early mornings. This can occur even if a pilot technically slept the required number of hours. The flaw lies not in the pilots, but in the assumption built into traditional regulation models that sleep automatically occurs, that it is high quality, and that the body is always able to recover effectively. The next section of the white paper examines why current regulation approaches have plateaued. FAA Part 117, for example, sets out important limits, but these limits were designed around general assumptions instead of pilot-specific data. They do not account for the timing of sleep, the individual's circadian rhythm, or the operational realities that affect real-world fatigue patterns. A pilot who is legal may still be sufficiently impaired, while another pilot with more favorable duty timing may be fully alert. This variable, and our ability to predict it, is what makes fatigue management such an important area for improvement. To close this gap, the white paper proposes a hybrid two-part solution. The first component is the integration of biomathematical fatigue models into scheduling systems. Models such as the SAFTE model used by NASA, the US military, and several international airlines calculates predictable fatigue levels by analyzing sleep history, circadian alignment, workload, duty length, and time awareness. These tools can highlight when a particular sequence of flights will put a pilot below safe alertness thresholds, giving schedulers the opportunity to model pairings before they are published. Airlines that have adopted similar tools report reductions in high-risk rosters and fewer fatigue callouts, simply because the system helps prevent unsafe pairings from ever reaching the line pilots. The second component in the implementation of the Comprehensive Fatigue Risk Management System, or FRMs, I told you we'd get back to those. While biomathematical models assist primarily on the scheduling side, FRMS provides a operational framework that involves pilots, dispatchers, safety managers, and leadership at all levels. An effective FRMS includes voluntary reporting programs, fatigue trend monitoring, specialized training or seridation science, and a mechanism for continuous data feedback. ICAO notes that airlines using FRMS have seen improvements in metrics such as stabilized approach rates, controllable rest periods or layovers, and overall alertness in the cockpit. Importantly, FRMS encourages open communication about fatigue without fear of discipline, which leads to better data and ultimately safer operations. My white paper emphasizes that fatigue is not random. It is predictable, measurable, and preventable. When organizations use the right tools by combining biomathematical models with a mature FRMS, airlines can create a safe culture that prioritizes pilot alertness in scientifically grounded ways. These approaches help reduce operational disturbances, minimize error linked to attention lapses, and support long-term pilots' health and performance. In summary, my white paper calls on airlines to move beyond regulatory minimums and towards productive, evidence-based fatigue management. Fatigue may be a persisting threat, but it is always one we are fully capable of addressing with the tools now available. Thank you.